Intermolecular forces in action. Like I mentioned earlier, if we didn't have any intermolecular forces, there would not be any solids or liquids, and all matter would be gases. And so that would make the universe a very different place. In liquids, two things that we observe that are functions or results of intermolecular forces are surface tension and viscosity. Let's talk about those. Surface tension. You can actually float a paper clip on water if you do it carefully. You can float a needle on water too, a sewing needle. And, some of you may want to try that at home. If you do, make sure that the container is very clean, has no soap in it, and that you don't have any soap or anything on your hands either. Everything's squeaky clean, otherwise it won't work. But you can float a paper clip on the water. What are paper clips made out of? Is that made out of balsa wood? That's made out of metal, isn't it? Do chunks of metal float in water? No. And this isn't shaped like a boat or anything. Why is that floating? It has to do with the surface tension of the water. The picture's not that great. You can kind of tell a little from the distortion here that the surface of the water is kind of being bent down. It's almost like somebody laying on a waterbed, right? They don't sink into the water of the waterbed because there's that plastic on the top, but it bends down and it holds them up, right? Well, it almost looks like there's a skin on the water that's holding up this paperclip. If you go to like the Kings River or someplace where there are water bugs, water skaters, and you can watch them, they skate across the water. It's really amazing. How do they walk on the water? Why don't they fall through? It has to do with the surface tension. So let's look at what that surface tension is. So here we have an illustration of some water molecules. And so this water molecule here in the middle is going to be attracted to the water molecules around it. And in this two-dimensional representation, we see there are 6 water molecules around this one. So it's being attracted to, held on to, stuck to these 6 molecules. This one at the surface, there's no molecules up here for it to stick to. And so it sticks to the ones next to it, and it sticks to the ones on the inside. But all of these forces are on one side of it, and so it's a kind of a lopsided pulling. And so there's this net inward force on the molecules at the surface. They're not pulled uniformly in all directions. They're pulled inward. And that sort of forms a skin on the water. And in order for something to break through that skin, it has to be strong enough to break those forces. So the stronger the intermolecular forces, the greater the surface tension. If you have very weak intermolecular forces, like in gasoline, has very weak intermolecular forces, then it's much easier for something to pierce the skin of the water. So a paper clip will not float on gasoline. I don't recommend that you try that at home, okay, because gasoline's kind of flammable. You could try rubbing alcohol maybe. It won't float on that either. Surface tension is the reason that water forms spherical drops. Now you might say, well, that's not a sphere. That's more like a teardrop shape. Well, yeah, that's because it's holding onto, I don't know if that's a leaf or a needle or what that is. But it's being pulled off of it. After it lets go, after it comes off of that, as it's falling, it forms a spherical shape. Water forms a sphere because in that way it can minimize its surface area. The skin can be as small as possible for the volume. This is kind of a cool picture. These are some astronauts on the space shuttle playing with water. And so in space, where there's no gravity, you can get much larger drops of water. What's holding that together? The intermolecular forces between the water molecules. And you could take more water and kind of just plaster it on the side of it, and it would stick and become part of that big bubble of water. Really kind of crazy. Viscosity is another result of surface tension. another result of intermolecular forces. Viscosity is defined as the resistance of a liquid to flow. Some liquids pour or flow very easily, and some pour more difficultly. Honey. You go to pour honey out of the container, and you're waiting, right? You're waiting for it to slowly come over, and finally, it goes down. Water doesn't do that, right? Water moves very quickly. And some fluids, like gasoline and alcohols, pour even faster than water does, and that's viscosity. High viscosity means it's resistant to flow. So honey has higher viscosity than water. Motor oil is more viscous than gasoline. And this word viscous kind of looks like the word vicious, but it's missing an I. So it's not vicious, it's viscous. So liquids are more viscous, flow more slowly. Viscosity is going to be greater in substances with stronger intermolecular forces because the molecules can't move as freely. So in something like honey, the intermolecular forces are much stronger. And so it's like you're trying to slide around, but you all have Velcro on. And so you're sticking to everybody, right? And you're trying to get through, and we're trying to move, but it's hard because everybody's kind of stuck. It's not a solid yet, but it's like getting towards a solid, right? Whereas something like water or gasoline, where the intermolecular forces are not as strong, they can slide past each other much more easily, and so they will flow. We probably hear the word viscosity the most in commercials for motor oil, and they talk about viscosity breakdown, right? The viscosity of your motor oil is important, because if the motor oil is too viscous, then it's not going to flow and coat all the components that need to be coated. And viscosity can change with temperature. So if you're going to be operating your car somewhere where it's really cold, you don't want your motor oil to get so viscous that it's almost a solid. But you also don't want it to be so inviscid, so low in viscosity, that when it coats the sides, it just runs off really fast. You want it to be in the middle so that it lubricates everything and keeps your motor from wearing out. And so they have all these different indications on the motor oil for what the viscosity is and what the temperature range, and it's all the good stuff. It's all very confusing. Here's a picture to make you hungry. Maple syrup. So when you pour maple syrup, especially if it's cold, it pours slowly. And see how it's like piling up there? Water doesn't do that, right? Water doesn't pile up like that. Now, it's not going to stay piled up. There's this little mound of syrup there. It's going to flatten out, but it's going to do it slowly. It's like it's moving in slow motion.